Welcome everyone to this week's Durham Geometry and Topology seminar. It's a pleasure to welcome Mauricio Bustamante from Cambridge University, and he will join the Catholic University in Chile in August. And he will talk about diffeomorphisms of solid tori.
Good, right. So thanks for the invitation. So let me before I start telling you anything about solid tori, let me give you some context for the sort of things I will be discussing here. So if you fix M, a compact manifold, I'm talking about smooth manifolds here, then you can look at its mapping class group, which is the group of path components of the group of diffeomorphisms of M relative to the meaning, like which are the identity near the boundary. So this is mapping class group of M, which is again the group of, if you like, isotopy classes of diffeos of M. Again, everything rel boundary here. So so this is a group. It's a and then sort of a natural question one has about this is about its finiteness properties. So with what finiteness properties does this mapping class group have? So for example, is it finitely generated? Or say finitely presented, or all these sort of things. Now when and so here's a bunch of things that people know already. So for example, Sullivan showed the following. So if this manifold is simply connected and is high dimensional, so the dimension is bigger equal than 5, and its boundary is empty, then this mapping class group is finitely presented, for example. So and also I think this is extended by Triantafilov when in the case when the fundamental group is finite, so one has the same kind of result in that situation. And also, but then as soon as you leave or you drop the finiteness of the fundamental group, you allow infinite fundamental groups, then bad things start happening. So, and this is something that was first observed by Hatcher and Sharp. And is that so? Even in the simplest case of which is the solid torus, so the simplest case with the simplest manifold, compact manifold with infinite fundamental group, they found that this mapping class group contains an infinitely many copies of C mod 2. This is a countably infinitely many of these guys. This provided the dimension of the solid torus is bigger or equal than 6. This does not happen in low dimensions, right? For example, when D is 3, this group here is trivial, I think. So this is definitely a higher dimensional phenomenon, and with this more things happen. I mean, this is a manifold with boundary, but then work of Farrell and Jones implies that if that these C mod 2s survive in the mapping class group of any closed, say, hyperbolic or even more generally non-positively curved manifold. Non-positively. Manifold M, right? So, for example, a torus, right? So, and the way maybe I can draw a very little picture here. Hope you can see it. The way you sort of implant these guys into the manifold M of negative curvature is sort of in the most natural way. So this is your manifold, and you have here a closed geodesic. Assume this is oriented, so you have the normal bundle is trivial, and then you can do sort of this one of these diffeomorphisms in this neighborhood of the closed geodesic, and since they are the identity on the boundary, just extend them by the identity outside the tubular neighborhood. And that they show that that kind of diffeomorphism actually is non-isotopic to the identity. So we have all these things, and then the question is, I mean, what is the explanation for this infinite generation when the fundamental group when an infinite fundamental group appears, right? So that's the question I want to address. So why? And since this the solid torus seems to be the manifold that is responsible for the infinite generation for a more general class of manifolds like closed hyperbolic manifolds or non-positively curved manifolds, then it seems like that's probably the best case to try to understand at first. So why is pi 0 diff S1 cross the infinitely generated? And I want to digress a little bit about how people prove this, or how people approach this from a classical perspective. So let me tell you point of view. So let me tell you how this is done with classical methods. So first you start with something that has nothing to do with manifolds or even with the solid torus. So you start with the following. You start looking at self-homotopy equivalences of S1 wedge, say G copies of Sn. This symbol homotopy automorphisms are, this is just self-homotopy equivalences of that space. And I require them to be fixed on S1, on the S1 copy. So that S1 copy is always, the map is always the identity on that copy. And then this you can map just by looking at, say cohomology of the universal cover, cohomology in degree n. You can map that to, so every self-equivalence is going to induce an automorphism of that homology group. So that's going to give you a map to G L G of C of the fundamental group of this space, which is the integers. So you take values here in the group ring over the fundamental group, which can be identified with just Laurent polynomials. So I'm thinking of T here as the fundamental group, the generator of the fundamental group of the circle, or of this space if you prefer. Okay, so this is just some sort of linearization map. Okay, now, and here comes, so here is, usually people take the induced map on classifying spaces, right? And you stabilize this by G, right? So you take, so here you can include matrices one into another by just putting a one on the, on the lower corner. And then you can take a limit of all those things. So that is going to change. So after taking limits, you get something. I'm going to just put an infinity here. And here you can also take stabilized by G. You can start adding spheres. And then, well, you can also stabilize by N by taking some fiber-wise suspension. So the point is that if you take the limit there, and in this context, you better take something that has good homotopical properties, so a homotopical limit. So over G and N, right? So you have this complicated object here and this other complicated object here. And now you make it even more complicated by taking the plus construction, right? But now when you are here, this is what Quillen defined as the K theory, or at least a component of the K theory of that ring. This is the algebraic K theory of the ring of Laurent polynomials. Now this one is also, this has a name. I'm just gonna call it A of S1. And this is the Waldhausen K theory of that space, right? Now you don't have to know much about this. The point is that there is this map, and this all these things are, I'm just giving you this as a definition of A of S1. And this map here is gonna have some homotopy fiber, which I will call, I will call, well, I would call nothing. I will call it homotopy fiber of L. Right. Now, what is the point here? The point is that the homotopy groups of this space, which are the K theory groups of this Laurent polynomial ring, these are finitely generated. This is something proved by using something called the Basseler-Swan formula for this ring. So that's going to give you a splitting of the K theory as two copies of the K theory of the integers, and those are finitely generated by theorem of Quillen. So this won't contribute to any, if there is any infinite generation in the homotopy of this space, it's not going to come from this one here, right? So it has to come from the homotopy fiber. But now it turns out that people managed to understand these homotopy fibers by something called trace methods, which I won't discuss here. And the point is that those are very efficient for doing calculations in this sort of setting. And what people find, so let me give you the two main results that are going to be relevant. So one is by Hesselholt, and the other one is Grunewald, Klein, and Mashko. So they can analyze these by some homotopy theoretic methods. They find something like this, homotopy fiber of L. So this homotopy group in degree 2p minus 2p, a prime, is going to contain infinitely many copies of symbol p, and that starts looking as the sort of group that appears in the mapping class group of the solid torus. Right now, what is the point of this? Well, the point is that this space here, although in principle has nothing to do with manifolds, it relates to manifolds by a very deep theorem of Waldhausen. So Waldhausen proved that this thing called A of S1 splits as two things. So one is some stable. So this is a space whose homotopy groups are the stable homotopy groups of S1. So in particular, these things are going to be finitely generated, the homotopy groups of this space, and it's something that is relatively easy to analyze, although the notation is that bad. And the other thing is something called the Whitehead space of S1, right? So again, if we are trying to so now we know that the infinite generation comes from here, and then from this splitting, the infinite generation of this space, well, it doesn't come from here, so it has to come from this Whitehead diff, right? So now the point with Whitehead diff is the following. So let me create a new page. Is the following theorem of Igusa, and is that there exists a D over 3, more or less D over 3 connected map from, so let's see, so B diff, I'm gonna put this symbol here, I will explain that in a second, S cross, S1 cross D minus 1 cross an interval to the loop space of that thing that I was calling Whitehead diff. Now this symbol here means that you're taking diffeomorphisms of this cylinder. So this is S1 cross the minus 1, and this is the interval here. And then these are diffeomorphisms, which are the identity on all these sort of this side here. So this exterior boundary, but they are allowed to move the top, right? So the top can be moved, and actually by restriction to the top, you get a map to be diff d, I believe, d minus 1, right? So in conclusion, so so from the previous page, I just told you the infinite generation in that space A of S1 comes from here, and it's detected by these so-called trace methods, right? But then by this theorem, that infinite generation should be also detected in this space by this theorem of Igusa, right? And then it's a matter of studying these spaces to actually get that infinite generation appears in this space, right? So in conclusion of all this, so if all this made no sense to you, just keep this conclusion in mind. So from these algebraic K-theory methods, one can find that 2p minus 3 of the B-diff real boundary of the solid torus contains these many copies of C mod P. And since this map here was D minus 3 connected, you get these 4 degrees, which are less than that. And that's how you understand this. And in particular, when P is 2, you get that the mapping class group. So when P is 2, this is pi 1 of this space, but pi 1 of the classifying space is pi naught of Diff. So that's the mapping class group, and that contains all these infinitely many C mod 2s, right? Everything in this range of degrees. So, okay, so I guess at this point, you and I agree that that was not a very geometric way to, understand this infinite generation. So, and since we agree on that, then
Henry, can I just ask about some of the couple of
sure.
things that we just said?
Yeah, sure.
First, I guess first of all, how did you? Maybe I sort of missed what you were saying about the map from the pseudoisotopy space to diffeomorphisms.
Yeah.
Like, how do you? I mean,
you just restrict to the top.
Yeah, but how do you know that?
How do you know what?
That that's non-trivial. That those.
Yeah. So that's what I was saying.
It's
not going to be enough. I mean, you need to, because there will be another map here. But to understand that, you actually have to know a little bit more. You need to know about some involution that appears in this space. Right?
Yeah. So
it's going to require some more argument. Yeah. So I'm not giving you full details for that. But so the point is that you need to analyze. So to decide whether it comes from here. So if it maps here, it comes from the thing on the top. Then you need to understand that involution essentially. But that's something that can be done in these specific cases, and especially because you are dealing with the infinite torsion groups here.
Yeah, what I'm a little surprised that you didn't mention Hatcher and Wagner, because I learned about this stuff from that paper.
Yeah, maybe. Yeah, actually, I missed probably messed up my quotations here. So when I say Hatcher, yeah, this is Wagner here. Actually, they didn't do it this way. Since now that you're mentioning, they did it using parameterized Morse theory. Yeah, so it's a different point of view, which gives you only
pi zero.
Pi zero, exactly. Yeah. So I don't know how you can possibly go to higher homotopy groups by those methods, but yeah. Mm-hmm.
Well, much harder, yeah.
So
okay,
yeah.
But yeah, so that way I would at least say is maybe more geometric though.
Right. Okay, I agree, because that's actually analyzing these possible singularities that appear in this Morse functions and things, and these fiber-wise Morse functions. Yeah, okay. So then let's say that there is another version to analyze just pi naught, which is also very geometric, and I am not mentioning anything about it. Yeah, agree.
But I mean, Igusa's proof is also using parameterized Morse theory, isn't it? That this map is connected, so it's somehow it is still appearing.
Yeah, but that's something that has nothing to do with the solid torus, right? I mean,
That's not that's not special to the solid torus, right?
Yeah.
All right, I'll let you carry on with your talk.
Yeah. Okay. Well, but again, I guess we do agree that what I just presented is not very geometric, and my goal is to provide another approach to that. So give an alternative approach to the infinite generation in pi k. This. Okay, so let me continue with that. So actually, let me state the. So I have the theorem stated here because it takes a while. So let me try to find it. I think it's this one, right? So this is the theorem that I will discuss. This is joined with. Oh yeah, I forgot to say everything here is joined with Oscar Randal-Williams. So again, there will be so we will be only able to analyze the solid torus for in the even dimensional case. As I was pointing out, this will be everything about high dimensions, so dimensions bigger or equal than 6, right? And the theorem is it's in the same flavor of the things that I was telling you. So for all these primes, and you have some range of dimensions in which this theorem will hold, we will see that these homotopy groups, the solid torus, will have you will see no infinitely generated p torsion, let's say, in that range of degrees. And as soon as you hit, and the first time you will see some infinitely generated p torsion is going to be, in this degree, and that I'm expressing by having this map from this infinitely generated group to this group in this degree. So these are exactly the same degrees that appear, in the previous discussion about using this K-theory business. So this will be an injective map here, so notice. So maybe let me remark that I was pointing out before that the Igusas from this method that I just mentioned before, you could get results for, up to degrees d/3, so the dimension over 3. If you see, this one is going a little bit further. This is going up to half of the dimension, right? So note, so we get a better range of dimensions. So note that we get degrees up to roughly d/2. Sort of a bonus result. Okay, so what is so let me tell you what the main ideas that go into proving this. Okay, so we'll create a new page here. So here's the key idea is the following. So it's to express the diffeomorphisms of the solid torus. So I'm now gonna be just talking about even dimensional solid tori as the difference between diff of a manifold that I will define in a second, called xg, and self-embeddings of the same manifold. So let me explain these symbols here. So the manifold xg is just the solid torus with a connexon of G copies, a connexon of G copies of Sn cross Sn. So say G here. So the manifold should look like, in low dimensions, it should look like this. So here is an X2, if you like. So that's the manifold. And this manifold has a boundary, which is the boundary of the solid torus, is S1 cross S2 n minus 2. And this boundary contains an S1 cross D2 n minus 2. If you think of this as glue together S1 cross the upper hemisphere and S1 cross the lower hemisphere of that 2n minus 2 sphere. Right? So you just pick one of those. And this thing here is what I'm calling half of the boundary of xg. Right? So here I'm taking, when I write this symbol, this is diffeomorphisms of this manifold, which are the identity near the full boundary. And these are self-embeddings of the same manifold, which have to be fixed on this part of the boundary. Right? But they are allowed to move the other half. Right? In particular, the other half could go to the interior of the manifold. Right? And when I mention this word here, express these diffeomorphisms as a difference, what I'm thinking is the following. So here's a more schematic picture. So suppose this thing here is my xg. So this top part will be representing the boundary. So this is partial xg. And then half of this is half of the boundary, right? And then suppose you have some embedding, some self-embedding. So the self-embedding is, so I'm gonna draw the image of that self-embedding here. So well, the self-embedding is gonna fix this part because I'm taking it here. And then, well, this other part of the boundary is allowed to go inside. So it's gonna go somewhere like that, if you like. And here is, this is the image of that embedding, right? Now, if you analyze what is left, this complement here. So this blue part, well, I guess you have to check, but the difference is essentially a copy of the S1 cross. This other part of the boundary is again S1 cross the 2 and minus 2, and you get like one additional coordinate here. So this is like a S1 cross the 2 and minus 1, right? So this is what I mean by the difference, by expressing these diffeomorphisms as the difference, because the difference between diffeomorphisms of this manifold fixing the full boundary and self-embeddings of such thing with this boundary condition, will differ just by having a diffeomorphism of this complement, right? Now, more precisely, what one gets is the following. So here's the Weiss fiber sequence. Weiss is named after Michael Weiss. And it's just expressing the idea that I mentioned. So you have there is a vibration sequence like this. XG and B embeddings XG. Now here you cannot take all embeddings. You need to take just some components of that space of embeddings, namely, so this symbol here now means like unknotted embeddings. because you need to guarantee that that complement is actually diffeomorphic to a solid torus. So essentially, you're taking all embeddings which are isotopic to a diffeomorphism. Right? So that's just some components of the space of embeddings. Okay, and this is a fibration sequence. Now, this is going to be very good news because of the following. So okay, so here's one remark. So this space here has an operation which turns it into a monoid. So, and the operation is by stacking. If you think of that space as the space of all manifolds diffeomorphic to that solid torus, then you can again take something like S1 cross D2n minus 2. You know, you decompose the solid torus as this with this. You know, you pull out this interval coordinate, and if you have two of those, then you can stack them together, right? So stacking turns this into a monoid, so you can take its classifying space again. And the good thing about this sequence is that it deloops, meaning that you can sort of continue it to the right. This won't be very important, but it's a technicality that is very useful for what I'm gonna say next. So the main point I want to point out about this is that this space is simply connected, right? And that implies that you can plus construct this fiber sequence. So okay, so this is probably too technical. I'm just gonna say that you can put plus here, and the fiber doesn't change, right? Now, why do I care about plus constructions? Well, it's because I can analyze the plus construction of this space. So let me point that out here. So now the key to these things is that, so first notice if G goes to infinity, if you increase the number of spheres you're attaching here, so increase the genus as much as you like, the boundary doesn't change, right? So you might as well just take the homotopy limit here and here, and you would get a fibration between stable objects with this sort of unstable fiber. So when G goes to infinity, the boundary is always the same. So sorry, S2n minus 2. And also, more importantly, well, not more importantly, but also this space is known. And the homotopy groups, when when you take the limit, are finitely generated. And this is a result of that. This follows from work of Galatius and Randal-Williams. And this is why this strategy is going to let us do something new. Because now we know one more, we know something about one of these spaces here.
Hey, can you say a bit more about I sort of didn't follow the thing about the plus construction. So maybe can you first of all?
Yeah, the point. So yeah, that's a little bit. I guess I can't give you a proof, but the point is the following. So if you have a fiber sequence like this, this is a general fact, and pi1 of y is 0, let's say, then you can plus construct the fiber sequence. Plus. But when you plus construct a simply connected space, you don't change it, right? So that would be like that. So I'm plus constructing here, right? This general result here is due to Berrick, I think, something from the 80s. Now you plus construct here, but this space was simply connected, so you may just...
Because that's a double B, it's simply connected.
Right, exactly. So pi1 of this is pi0 of B, but B of something is connected, right? And then now you can loop this thing back up, right? And then you get again this fiber sequence. So that's the point. Is that clear? So everything boils down to this sort of more general statement. Okay,
Great,
so
thanks. Yeah, that's
okay, so that now the point is here. When you pass to this limit here, when you let the genus be, as you know, very large, then this space becomes homotopy equivalent to some infinite loop space of some Tom spectrum. But again, these in spite of the notation, these are rather easy objects to analyze, especially if you just want to say things, of this quality, like finite generation and things like that. So you can show rather easily that this space has finitely generated homotopy groups. And that's good, because then the conclusion of this discussion here is that now we know the infinite generation in the homotopy of the diffeomorphisms of the solid torus comes from, it has to come from the space of embeddings with this funny boundary condition. Okay, so now, okay, so then now we have to analyze this space. Let's see. Okay, so then my next goal is to see where the infinite generation in this space comes from. Okay, so, and this is going to use, well, I'm going to call this a linearization map. But although, I mean, it's not entirely obvious what I'm calling it this way, but anyway, so it's, and here's the map. You take, so you're looking at embeddings of XG, and you can just map it to the group of components. So this is the just isotopic classes of embeddings with this boundary condition, and also with this constraint, which is that they have to be isotopic to a diffeomorphism. And again, I don't really care about these spaces. I care more about its classifying spaces. So I can just induce a mapping on classifying spaces. And again, by the previous discussion, I don't really care about this space. I care more about its plus construction. So I plus construct this. And the fiber of this plus construction, I'm going to give a name, which is delta G. Right? And here's the first claim about this. And is that the homotopy groups of this guy, of the base, plus constructed, are finitely generated. So this, if now everything here is going to be in some stably, right? Like you might just as well take the homotopy co-limit in this vibration. So now this would be complicated to explain in full detail, but so here are the two main ideas to prove this. So this uses the following. So first, you compute the mapping class group. So say this group of isotopy classes, and you compute. By that I mean you put an extension, and you prove that there is an extension. So here's the first thing. There is an extension of this type. So it's so this is the end homology of XG. So this is just Z to the 2G. So that's very mild in terms of finite generation, and some subgroup of the n+1 homotopy group of the orthogonal group, right? So this S is just to indicate some, like the image under the stabilization map from SON to SON+1. which is also, I mean, these groups are very mild for this discussion. They are finitely generated in particular. Now that maps injectively in pi 0 so this is pi xg, and it surjects onto this is something that I'm calling omega g, and omega g is a finite index subgroup of the group of automorphisms of pi n xg. And let me put two more symbols here, lambda and q. So so this map here is, so you take a self-embedding of this type, and then you see what it does on the nth homotopy group of xg, right? So now, since these are all smooth embeddings, these embeddings preserve, so not only they give you an isomorphism of that homotopy group, pi n of xg, but they also preserve more data, which is what I'm calling here lambda and q. So this lambda refers to a bilinear form you can put on this, which has to do with the following. So if you think of elements here, they should be represented, or you can represent them by immersed n spheres in xg, and then lambda is counting intersections between, is the intersection product between these n spheres, and q is counting sort of self intersections of those immersed n spheres. So roughly that's the structure you preserve. But then you realize that pi n of xg, if you compute that group, I'm not sure if I said this or if you have noticed it already, but this xg is homotopy equivalent to S1 wedge 2g copies of Sn, right? So it's sort of easy to compute that specific homotopy group, and that is you can make it isomorphic to C T inverse to the 2g, right? So this, in the end, you can just think of it as some unitary group. So this is some group of matrices that I'm calling U sub g, which preserve some bilinear form and some quadratic form, right? So in some cases, this coincides with the symplectic group over that ring, right? Okay, so you have this extension, and that is the first thing one should prove. And then the point is, again, this won't contribute much to the, if there were any infinite generation in this space, this won't be responsible for it. So one has to sort of study this one here. And so that's the second thing one has to analyze. So let me make a new page. So the second fact is that the homotopy groups of B of omega G plus are finitely generated. Again, G is supposed to be, very large. And this is also kind of difficult and uses very recent technology. So the point is that since this was a subgroup of finite index of this unitary group, then we have so we can just, I mean, the result will follow if we prove it for the unitary group. So the point is this is the plus construction of this is identified with something called Grothendieck-Witt theory of this ring. This is like, I won't tell what this is exactly, but this is like the K theory of not only projective modules, but modules with a quadratic structure on it, right? So it's some algebraic thing that I will tell you how to analyze it later. And this is due to Hebestreit and Steinle. Right. Now, the point about this again is that there is work of these two people plus 7 more authors, which puts this space into a fiber sequence where it maps to L theory and has fiber the K theory of that group ring, and then the orbits under the action, given by duality. Now, this thing here, if you're these are related to the groups that appear in surgery theory. They are not exactly those, but it's related to it. And using actually that relation, one shows that, and actually Ranitsky and Shanison show, and in the end, Kerber and Milnor show that this is finitely generated.
Do you mean because that's symmetric L theory?
Right. Yeah. Well, it's actually not even. If you see the theorem of these guys in this document they have now in the archive, you can relate it to symmetric L theory. So in some degrees it's symmetric L theory, in some other degrees it's not. But in all cases you can study it. So
you can
and then
apply splitting to it.
Sorry?
You can still apply splitting to it, is what it's saying.
Yeah, you can apply the Shanison splitting theorem to those groups. And also, and here this is something that appeared already in this talk. This is, using Basler-Swan, you have a splitting of these groups as 2 copies of the K theory of the integers, and those are finitely generated. So this, in conclusion, this guy has finitely generated homotopy groups, and hence this space here is going to have finitely generated homotopy groups, right? So then the conclusion, if we go back, oh no, that's not meant to. If we go back here, so the conclusion is that the infinite generation in this space has to come from this homotopy fiber, right? So the next thing is to explain how that is done.
I have another question. It's probably slightly stupid, but what can you talk about the difference between this? I mean, you've got isotopy classes of embeddings that are isotopic to a diffeomorphism. So what's the difference between that and just looking at diffeomorphism, pi 0 of diff of this space? Just the boundary condition, or?
But that's exactly captured by, if you see that Weiss fiber sequence, the difference is going to be diffeomorphisms of that complement. That's exactly, if you look at pi, if you had the Weiss fiber sequence, and you look at the induced map in pi 0, you look at the longest axis sequencing homotopy for that thing.
Yeah, right.
So you're going to have to analyze, what comes from pi 1.
So it's subjective, but there is that kernel.
Oh yeah. That's subjective by definition. Yeah. But you still may have some.
Okay. Yeah. Thanks.
Yeah. So okay. So then the point is this homotopy fiber that I was calling delta G. Okay. So let me to study the homotopy of that homotopy fiber, we will use some other general fact, some kind of generalized Fourier-Witch theorem, more or less, which is the following. So if you think, suppose you have a space. So let me assume here that pi 1x is perfect, and x is path connected. So you can look at the classifying map for its universal cover. This is the pi 1x, and then universal cover, and then you take the corresponding thing but plus constructed, and you're going to have some homotopy fiber here. Then here's the general fact. If pi k x tensor C localized at P is 0 for, say, k less or equal than L, and say maybe 2, bigger than 2, then pi k of the fiber is going to be 0 in that range of degrees. And well, okay, maybe it's better to put an strictly less. And pi, and there exists a isomorphism between h, well, the coinvariance of pi 1x acting on pi L of x to, oh, and I forgot to tensor this with C localized at P to the L homotopy group of the fiber. So this is telling you how, when you localize, how to detect the first non-trivial homotopy group up to, you know, torsion, P torsion in this case. So so I will just use this fact. I will not prove it or anything. But the point, what you have to observe here is that we want to analyze this fact to the original fiber sequence, right? The one that contained this delta G, right? So that reduces the problem to verifying this condition for the space without plus construction, right? The point is, when you plus construct, the homotopy groups become very difficult. But in this case, at least we can try to understand the first time this infinite generation phenomenon is going to appear without taking this, or before taking the plus construction. So this reduces the problem to understanding, or rather to computing pi k be embeddings of xg as a module over the, you know, the mapping class, the group of isotopy classes of xg. Okay, so I'm saying this because this, because if you can compute as a representation over this group, then you have a chance to compute the coinvariance, right? And hence you will be able to compute. So in this case, F would, in our case, F would be like delta G, right? Okay, so let me tell you quickly how this is done, and then. So the point, the whole point here is that, so to do this, one has to build, so use Weiss fiber sequence in the top category to build a map from, I can give more details later. It's just that I feel I'm gonna go over time, and I won't get to the point that I want to get at. So this is embeddings. So the space I'm interested in to homotopy automorphisms rel the full boundary to xg, right? So you're gonna be able to build this map. And the homotopy fiber of this map, so let me call it something like AG. And one can show using surgery theory and something called the Morlet disjunction theorem that pi k of AG is isomorphic to the pi k of some mapping space, some kind of normal invariance space, xg to g mod O. If you don't know what this actually means, don't worry too much. The only thing you have to know is that this is these are finitely generated groups. because the homotopy of this space is all known, right? So the conclusion here from this would be that, well, first of all, since this won't contribute to finite generation, the infinite generation has to come from here, right? And secondly, you can use this sequence to actually verify this hypothesis of the general fact. So, obviously that would be a little too complicated to do here, but that's the point I wanted to get at. The point is now that the infinite generation in this space of embeddings, or in its homotopy, actually I meant to say in the homotopy fiber I care about, comes from this space of homotopy automorphisms, or from its homotopy. But now here we are in very good shape, because, for example, you have a map from homotopy automorphisms real boundary of this space to homotopy automorphisms, which fix not the full boundary, but just as a circle factor of the same space. And these ones are just homotopy automorphisms fixing S1 of S1 wedge 2 copies of Sn. And the homotopy groups of this space are not too complicated to estimate, and some of them you can compute. So this, for example, a pi k of this space, S1, Sn, 2G. This is isomorphic to something very, very concrete, which is only about the homotopy of the space Xg. So this is, let me have it here. Yeah, it's a hom over C T inverse of pi n Xg, pi n plus k Xg, right? So you can fully compute these things. And then, so for example, if you want to be very specific, in some of these degrees, you can actually tell what these guys are. Of Xg. This is, for example, isomorphic to H. So if you call H the nth homology of Xg, then this is isomorphic to H tensor H tensor the first. If you see here, this would be like pi n plus 1 of Xg, but Xg has this decomposition, so the first stem is going to appear here. So pi 1s, and then you propagate that with that circle. And this group here is actually Z mod 2, right? So actually in these degrees, the Z mod 2s in fact come from this factor. So you have to analyze how much of this infinite generation here is going to be hit by this map. But then, you know, that's something you can do, and then you essentially reach the point where you can use this general fact to deduce you know, to finally detect all the infinite generation in the homotopy of this space. And in, you know, just following through what we did, that's gonna survive, if you like, or it's gonna be mapped to the homotopy of the diffeomorphisms of the solid torus. I think I'll stop here, since I feel like I'm going over time now. So thanks for your attention.